And let's give it a shot. Okay, so question 16.6 says predict the products for each of the following reactions and propose a mechanism that explains the formation of each product. Start with B, and if you look at B, you see that it is a fully conjugated system. However, those two double bonds aren't identical, are they? No, they're not, because if you look at the first double bond, it's tri-substituted. It's attached to 1, 2, 3 carbons. Whereas the other double bond, if I highlight it in green, it is tetrasubstituted. It's attached to a total of 1, 2, 3, 4 carbons. And therefore, we could add HCl to either one of those double bonds to produce an allylic carbocation. Again, when we add HCl across one of the double bonds here, we're not concerned with Markovnikov addition. What we want to do is make an allylic carbocation. Therefore, if I look at this double bond, I want to add the hydrogen atom here so that I'll end up with the positive charge on this carbon, which will produce an allylic carbocation. Let's draw the arrows that show that allylic carbocation being formed. So my double bond is going to take this proton, and let's draw that allylic carbocation. So it's going to look something like this. We have our double bond here, and then we're going to have methyl group down here. Now I've added that hydrogen here, and so I have the positive charge over here. Now, I can draw a resonance contributor because I have an allylic carbocation. Let's draw the resonance contributor. Let's take the blue pen. We'll say, well, the pi electrons could be over here. And so if that happens, or if we draw that other resonance contributor, it's going to look like this. Or we have something that looks like this. And now our positive charge is going to be over here. We still have this proton over here, but now we've just drawn the other resonance contributor. And so you can see that we have the positive charge in two places. Okay, now that we've got that, why don't we draw the products of nucleophilic attack on both of these carbocations? So I'm just going to erase this curved arrow. I think everybody can draw a resonance arrow for an allylic carbocation. And now we're going to draw our chloride ion, which will be our nucleophile. And the chloride anion is going to attack at this carbocation, and it's also going to attack at this allylic carbocation. Both of them are allylic. So we end up with some products. Let's draw the product. So the product of the first addition, which is the 1,2 adduct, is going to look like this. Oops. Try to draw it a little prettier, where we have chlorine here, like that. Now, what about this compound? We have a stereocenter here. Is it racemic, or do we get R, or just the S? Well, remember that a carbocation is trigonoplanar. And so when the chloride ion comes in and attacks, it can attack from the front face of the molecule or the back face of the molecule. And so this would be a racemic mixture, a racemic. When it attacks this carbocation, again, it can attack from the back or the front face, but you don't get a stereocenter because you have two methyl groups on here. And so we end up with this compound. So there we go. So that's our 1,2 adduct and our 1,4 adduct when we add HCl across this bond to make an allylic carbocation. However, we're not done, are we? We can also add HCl across this carbon-carbon double bond to make a allylic carbocation. Let's do that on this page. So we didn't really use this at all, and we're not going to use it on this page either. Let's continue on with B. So now we're going to do the same thing. We're going to add HCl, but we're going to add it to the other double bond, the one on the left. And so we want to add the hydrogen atom here so that we end up with a positive charge here, which would give us an allylic carbocation. So, and you can draw, I like to draw the curved arrow going through the carbon where the hydrogen is going to be attached. So let's draw what this allylic carbocation is going to look like. And it's going to look something like this, where I have my positive charge here, and here's my hydrogen atom that I added. And of course, we can draw a resonance contributor for this because we have an allylic carbocation. That goes all the way back to chapter 2 in Organic Chemistry 1. So we draw the resonance contributor, which looks like this. So now we have the double bond. Oops, I drew it in the wrong place. Double bond here. And we have our methyl group here. And now we have our positive charge over here. So we have two allylic carbocations. Again, just put this proton in for educational purposes only. And now we have our chloride ion over here, and it can attack at both of those carbocations. So it can attack from either face of the molecule here. We're going to end up with a stereocenter, aren't we? So we end up with this, the double bond here, and I have my chlorine here, but this is a stereocenter. But again, the chloride can attack from either face of the molecule. And so this would be racemic. So we'll put here racemic. And it could also attack here. And of course, this will not give us a racemic mixture because you've got two methyl groups here. So we do not produce a stereocenter in this case. Let's draw the molecule. It's going to look like this. And we're going to have our chlorine out here. And there you have it. So you end up with all four of those products. Let's go back. You end up with this product, which is a racemic mixture. This one, which is not racemic because this is not a chiral center. Sorry, this is not a chiral center. Then if you add across the other double bond to make the other allylic carbocation, you end up with this compound and this compound. So if you're wondering, Mr. Dion, would you make a total of 6 compounds, 2 racemates and 2 compounds that don't have a chiral center? The answer is yes. You end up with that many compounds. 2 1,2 adducts and 2 1,4 adducts in this case. So what we're going to do is we're not going to answer this question right away. Question 16.6b. I'm going to give you some time to work on that in our next break, and then we'll come back and we'll try that problem. Let's talk about this whole idea of getting a mixture of 1,2 adduct and 1,4 adduct. Is there anything that we could do to prevent from getting a mixture, or is there anything that we could do to produce one of these regioisomers in a greater amount than the other regioisomer? Because let's face it, if you make, racemic mixtures and, equal mixtures of everything, then it gets really difficult to separate the compounds, and the chemistry is not that useful. Well, check this out. If you try to add HBr across 1,3-butadiene, and you do the reaction at 0 degrees Celsius, you get mostly the 1,2 adduct. However, if you do the reaction at 40 degrees Celsius, you get, by and large, the 1,4 adduct. So we call this kinetic, we call the 1,2 adduct the kinetic product, and we call the 1,4 adduct the thermodynamic product. If you're wondering, well, why do you call one the kinetic product? So again, we call this the kinetic product. And we call this one the thermodynamic product. It's because the major driving force behind the formation of the 1,2 adduct is kinetics. And the major driving force between the formation of the 1,4 adduct is thermodynamics. Let me show you what I mean. Let's take a look. The formation of the 1,2 adduct forms faster. If you look at the first step for both of them, the activation energy is identical, because it doesn't matter whether you're forming the 1,2 adduct or the 1,4 adduct. The first step is the exact same in both of them. The first step just involves the reaction of HBr with the double bond. The rich get richer in this case, and you end up just forming this allylic carbocation, which you see right here. So that's the same for both of them. However, we know that there is resonance, isn't there? Right? We know that there's another resonance structure for this where we could have the double bond here and have the positive charge on the end. So if the molecule doesn't rearrange, or sorry, if we just look at the carbocation the way it is here, I shouldn't say rearrange, but if we just think about this carbocation, this secondary carbocation, well, you see the activation energy to get to the 1,2 adduct is lower than the activation energy to get to the 1,4 adduct. Well, why would this activation energy be higher? Because this, the top of this one here is when we have the nucleophilic attack on this carbocation, and over here, it's when it's on, let's see here, this carbocation. Which one of these is going to be more stable? It's going to be this one because this one is secondary allylic, and this one is primary allylic. So it's going to take more energy to get up here. But then if you look at the product of after the nucleophilic attack occurs, the product that results from the primary allylic carbocation is more stable. Well, shoot, why would that be? It's because if you look at the carbon-carbon double bond, it's di-substituted. It's more stable than the carbon-carbon double bond in the 1,2 adduct, which is only mono-substituted, right? It's only got one carbon attached to it, whereas the other one has two carbons attached to it. So since the activation energy for the formation of the 1,2 adduct is smaller, we call it the kinetic product, because we can run this at low temperature because the activation energy is so high. Whereas if we're at a higher temperature, then we provide the molecule with enough energy to go over the higher activation energy to give you the 1,4 adduct. Summarized, it says it right here. The 1,4 adduct is more stable because it's the more substituted alkene. And at higher temperatures, there's going to be an equilibrium. Check it out. At higher temperatures, the formation of the products is equilibrating, right? You're at higher temperature, and so the bromine can actually leave from here, regenerating the carbocation, which can produce the other allylic carbocation to give you the 1,4 adduct. And so in that case, the product that is more stable is going to be the major product when you're at a higher temperature. Now, why does the 1,4 adduct form, the 1,2 form at a lower temperature? Why is it faster? Well, it's because of something called the proximity effect. We know that proximity means closeness. And since carbons 1 and 2 are closer than carbons 1 and 4, once you get that protonation occurring to produce this allylic carbocation, since the bromide is already there, it can attack at carbon number 2, and that's the proximity effect. And that's why at lower temperatures, we end up getting the 1,2 adduct. However, just reviewing, when you're at a higher temperature, then the bromide can leave. So you're at a high enough temperature, there's going to be an equilibrium where this leaves. Okay, so draw my equilibrium arrows properly, but you end up making this carbocation again, which can rearrange or undergo, produce this resonance structure, which can undergo nucleophilic attack to produce the 1,4 product. So thermodynamic versus kinetic control. Well, with all that in mind, let's try a problem here. It says predict the products for this reaction and determine which product is going to predominate. Well, I've chosen two problems. I chose one that we're doing at 40 degrees Celsius, and so the thermodynamic product is going to predominate. And then I chose another one that's at 0 degrees Celsius, so the kinetic product will predominate. Well, let's take a look here. So what are we going to do? We have a diene. It's conjugated, right? It goes double, single, double. So what we want to do is we want to add HBr, and the proton is going to get added to one of those double bonds. Now this molecule is symmetrical, so it wouldn't matter which one we used, but it's going to add it in such a way that we end up with an allylic carbocation. And so if we look at this double bond here, if I label this carbon in red and this carbon in blue, which carbon is going to take the proton in order to produce an allylic carbocation? Should the proton go on the red carbon or the blue carbon? If I want to make an allylic carbocation. The red or the blue? Could anybody answer that for me? Anyone? Well, if I want an allylic carbocation, that means that I would want to have the positive charge here to make an allylic carbocation, which means I would want to add the proton to the red carbon. So let's do that. Let's draw a mechanism that shows the proton being added to this carbon, which is going to give us an allylic carbocation. So let's draw that allylic carbocation, which is going to look like this. Keep in mind that we already added this proton here. Well, since we have an allylic carbocation, we can draw a resonance structure. Another resonance structure, I should say. So what's that going to look like? We're going to move this pi bond over here, and we end up with another allylic carbocation, which is going to look like this. Okay, so these are my two allylic carbocations. And now my nucleophile could attack either one of those carbocations. So I'm just going to delete the resonance arrow, and I'm going to draw an arrow going down. Our nucleophile is going to be bromide. So we'll draw a bromide here, draw a bromide here. And let's draw the nucleophilic attack. It's going to look like this. Here it's going to look like this. And let's draw the products. So here we end up making, oops, that's not very pretty. There we go. We end up with our double bond here. And we end up with the bromine here. Now we have a stereocenter here. And so we're going to end up with a racemic mixture. So racemic mixture in this case. And then when it attacks at the bottom, we're going to end up with this compound. We have the bromine down here. And of course, that's also a stereocenter. So this is also going to be racemic. Now, if I number the carbons, if I number these, let's use the green pen. If I call these 1, 2, 3, and 4, you can see that the hydrogen here, and here, and here, the hydrogen in the first compound is at carbon number 1, and the bromine is at carbon number 2, whereas in the second one it's at 1 and it's at 4. So that means that this is the 1,2 adduct. So this is the kinetic product. And this is the 1,4 adduct. And so this is the thermodynamic product. Since we're at 40 degrees Celsius, thermodynamic product is going to be the major product. Major product. And therefore, this will be the major product. Major product. Just like that. Nothing to it, huh? No, it's actually kind of complicated. All right, it's definitely going to take some practice to master this. Let's try 16.9b. So, does anybody have any questions about this? Any questions about this problem?
I was actually going to ask.
Yeah, go for it. Ask me anything.
So, I honestly am a little bit confused where you would start, because once you start, then I'm following you. But like choosing where the hydrogen goes, like your first step, I get a little bit stuck right there as to how to make the allylic.
Yeah, so an allylic carbocation, so this goes back to chapter 2 of Organic Chemistry 1. Looks like this. You have a double bond, and on the next carbon, which is the allylic carbon, you have a positive charge. So you just have to make that. Thus, when you look at a molecule, if you have a conjugated system, now this, again, this molecule is completely symmetrical, so it doesn't really matter which double bond you use. You could either add a hydrogen to this carbon that I'm highlighting in red, or this carbon that I'm highlighting in blue, right? You could do either one of them. If you were to add it to the carbon in blue, right, if you added a hydrogen to that, what would it look like? Then the molecule would look like this. You'd have the methyl group, but you'd also have a proton, and so your positive charge would be here, right? Whereas if you added it to the red carbon, then you still didn't touch anything on this side. You have the hydrogen over here, and there already is one there to begin with, right? There's this hydrogen, which is still there, okay? But then you would have the positive charge here. Which one of those is an allylic carbocation? The one that's in red goes double bond, single bond with a positive charge, right? That's an allylic carbocation, right? If you go up here, what I have here is what you see right here in this system, right? It's a double bond. Let me draw it in red. It's a double bond and a single bond attached to it with the carbocation, right? What I have highlighted here is what you see right here, an allylic carbocation. Whereas the one in blue, there's no allylic carbocation in there anywhere. There's a double bond, but there's no positive charge here or here. Therefore, there's no allylic carbocation. And you want to add the proton so that you end up with an allylic carbocation. Therefore, this is not going to happen, whereas this is going to happen. Does that help?
Holy cow, yes, thank you.
Okay, so that's what you got to do. All right, so let's try this one. And now that we've gone ahead and drawn the carbocation, right, Lindsay? The next thing you want to do, and I'm just going to convert everything into black pen here. So let me just select all this. There we go. So the next thing you got to do, now that you've got the allylic carbocation, is you've got to draw the resonance structure. And again, this goes back to chapter 2. It was the first resonance structure I ever taught you how to draw. Was you take this and you show how these electrons are delocalized across the entire system like this, so that you can draw this resonance contributor like that. Okay, so we do the exact same thing here. We take this pair of electrons, we move them over here, and when we do that, we end up with this resonance contributor where we have this, and then our positive charge is going to be up here. So now the last part of the problem is just showing the nucleophilic attack. And the nucleophilic attack can occur at either one of those carbocations. So we take our chloride ion. I'm not going to draw the full Lewis structure just in the interest of time. I'm going to delete this resonance arrow because I don't want to mix arrows. So we get a nucleophilic attack. It's kind of a crappy looking arrow. We get one look here, and we get another one here, and we draw the products. So for this one, end up with this. I'm not going to worry about the stereochemistry this time, doesn't matter. All the question is asking about is kinetic and thermodynamic product sugar. Can draw better if I'm remembering than that, even on an iPad. There we go. So if I call this one, I'll call the first one A. I don't know why I wrote the letter B. I'll call this one A and I'll call this one B. Could anybody tell me which one of these would be the 1,2 adduct? Would it be A or B? Yeah, absolutely. It's A. So if we're counting our carbons here, we count them like this. Oops. 1, 2, 3, 4. You can see that in this one, we added something at carbon 1 and something at carbon 2. So this is the 1,2 adduct, which is the kinetic product. And then in this one, we added something here at carbon 1, 2, 3, 4. So this is the 1,4 adduct. And this is the thermodynamic product. But since we're doing the reaction at 0 degrees Celsius, kinetic is major. and therefore the major product is going to be A. Does that help with the numbering, Emily? So you always start on one of the carbons of the conjugated system, one of the carbons of the double bond system. Yeah, you can do it either way, and you're going to get the right answer. Yeah, I mean, this molecule is symmetrical, right? But if you were to go back to this example where it's not symmetrical, like this example that we looked at before, okay, it wouldn't matter if you numbered it, 1, 2, 3, 4, like that. Okay, it wouldn't matter. This, you have a hydrogen here, so this would be, of course I labeled it backwards, but this would be 1, 2, 3, 4. So this would be the 1, 2 adduct, and then this would be the 1, 2, 3, 4. This is the 1, 4 adduct. The same thing every time, right? That's what they're demonstrating on this slide, which I just copied from the textbook. Okay, you have 1, 2, 3, 4. So you always number the conjugated system, and then you end up with something on carbons 1 and 2, and something on carbons with something on both carbons 1 and 4. Does that explain it a little bit more? And if you have any other questions, don't hesitate to stop me. What does that say? Are those the only conditions that would be that would what the major product would be? I'm not 100% sure what that means, but okay. All right. Well, if you have any other questions, don't hesitate to stop me. But what time is it? All right. Let's talk a little bit about pericyclic reactions. Let's just, do you always make the allylic carbocation based on 1, 2? It wouldn't matter if it's 1, 2, or 3, 4, because Emily, you don't want to think about the 1, 2, and 3, 4 in terms of nomenclature. Just think about it in terms of numbering the carbons that are undergoing the reaction. So if the reaction is occurring at carbons 3 and 4, the way you have it drawn, just flip the numbers around. Okay, yeah. So if it's 3 and 4, just reverse them, right? I could have drawn the exact same mechanism on this side of the molecule, right? It would have been identical, and that would have been on carbons 4 and 3. So if I did that, I would just change them. I just would have changed them to 1, 2, 3, 4. Can you go over how based on the temperature you get from me? Yeah, so the rationale for both, Sandrina, the easiest rationale is really nothing more than this. Thermodynamics means you're always going to make the most stable product. The 1, 4 adduct is the thermodynamic product, right? And this is the kinetic product. The 1, 2 is kinetic. Why is the thermodynamic the 1, 4? Because it's more stable. Remember, as you have more substitution on an alkene, it becomes more stable. This alkene has 2 R groups on it, whereas the 1, 2 adduct only has 1 R group on it. So this is more stable, and therefore it's the thermodynamic product. Think about kinetics deals with speed. How fast can we get the reaction to occur? And if we look at the nucleophilic attack in the 1, 2 product, think about it. You protonate at carbon number 1, you form a carbocation at number 2, and before anything can happen, before you can get that to happen to make this, the attack just happens right away at carbon number 2. And so it's faster. And that's why we call that the kinetic product. Does that help? Okay, there we go. So kinetics deals with the speed, and the thermodynamics deals with the stability. Somebody says what the temperature range would be in determining kinetic versus thermodynamic. For our class, I think that everything is either 0 or 40 degrees Celsius. If you go back here, here they use 0 and 40, and in the other example, they use 0. So 0 for kinetic, 40 for thermodynamic. Are there probably ranges outside of that, Nicole? Yes, probably. For our textbook, that's all they use. All right. Well, let's see. Let's go back here. There was a question we didn't do. Which one was it? It's 16.6C, right? 16.6C. So predict the product. Let's go over to a blank document here. So let's find some space, some blank space. I got a blank space, baby. All right, so let's see here. Let me back up in my notes. I don't want to make a mistake here. It was 16.6, question C. It's this here, where we have an unsymmetrical conjugated system. Right, here's our conjugated system. Okay, and they're saying that you're adding HBr. Oops. You're adding HBr. Now, they're not talking about, this question has nothing to do with thermodynamics or kinetics. The question just says, draw all of the possible products. So where would you add a proton in this molecule? This molecule is not symmetrical. But if we added a proton either here to this carbon, you would end up with a positive charge right here. And if you added a proton to this carbon, you would end up with a positive charge here. So if you added a proton to the green carbon or the yellow carbon, you end up with an allylic carbocation. So what I want to do right now is take another break. I want you to try this problem. I want you to draw the protonation at the yellow carbon. I'll help you out. You're going to end up with a proton transfer here. So you're going to end up making this allylic carbocation, where you have the positive charge here. So what I want you to do is to draw the other resonance contributor and draw the products of the nucleophilic attack. Then I want you to try to do the same thing at this carbon. So there's going to be at least 4 different products, okay? I'll give you a clue. All of them are racemic in this example, but I want you to try to draw all 4 products. So we're going to take a short break, and everybody's going to give this one the old college try.